construct the MOT of any molecule, your first job is to find out the point group of given molecule. For example, as a case for AB2, I have preferred the molecule BeS2. We all know that the geometry of the molecule is linear, right? Now, first of all, it is linear. Second, this molecule is having center of inversion. I is present. So what possible point group would be? D infinite H. Okay, D infinite H. Now this is a character table for D infinite H point group. Okay, if you will see here, in some of the symmetry element, infinite is mentioned. So it is really difficult to find out or to apply the reduction formula in this case, right? So what do I do? First job is we need to segregate the axis. So now remember, here I have taken Z axis, this one, then Y, then X. I already told you that to pick up any axis of your choice, it's a freedom for you. Okay, but you have to keep it same throughout the study. It should not be happen like for any symmetry operations we have taken x-axis in this direction and later on we are switching to some other axis. No, whatever the axis preference you have taken in the beginning, the same strategy you are going to apply throughout the molecule. So here z-axis is in this direction, then y, and x is perpendicular. Okay, now see, one concept is there where you can apply the descending method of symmetry, right? So I told you, if you will apply D infinite point group, then it is a bit difficult to apply the reduction formula, because in that you need to multiply with the help of infinite. To make it more simpler, what we can do, we can take a subgroup from the group which is having the symmetry element present. For example, D2H. I have taken a subgroup D2H to explain the D infinite H. This is called descending method symmetry, because आप एक higher order of point group से lower order of point group को ले रहे हैं. ये क्यों लेते हैं? Always remember, it is for your convenience, just to make it easier to conclude the reduction formula and solve equation. That's why we used to prefer. कोई भी group ले सकते हैं? No. What you can take it, you have to find out the subgroup which is already present in a group, or you can say there in a big or higher point group, there will be some subgroups or some point groups which are already been present, and they can notify the basic sets of molecule can be preferred as a subgroup. So here I have taken that D2H. Okay, now to represent the BeS2, I have taken the two circles. One is from the green and another is from red one. These are representing two H atom. Okay. Now see, if you will solve this, right? I told you how to solve this. If you will solve this, you will notice with respect to E, whether both the atoms are going to be changed. No. With respect to E, basically what would be happen? Your molecule is going to be, your atoms are going to rejoin the same conditions, right? That's why I have written it here C2. Now along the z-axis, if you will perform the C2 operations, then of course both the atoms are going to be remain unchanged, and that's why here I have written the contribution 2, because these two are going to be remain same during the symmetry operation C to Z. You see this Z is going to be passed through along this axis. If you are going to rotate through C2 axis, whether they are going to be changed? No. That's why I have mentioned here the contribution is 2. What about C2Y? See, Y axis is perpendicular to the XZ plane. So basically C2 is going to be passed through from this particular point, this one, right? So in that case, green will occupy the red one and the red one is going to occupy the green one. That's why the contribution will be 0. The same thing is going to be applied with respect to C2X. That's why I have written here 0. Now, let us find out with respect to the center of inversion. Center of inversion here. If you will rotate, what would be happen? Again, the whole molecule is going to flip, and again the contribution is going to become 0. Sigma XY. sigma xy is the plane which is going to be perpendicular to the z axis. So means you are going to pass a plane with respect to this. For example, I will take the pin now. Wait, what would be xz actually? Xz will be something like this, right? Now see, in this case, basically this molecule is going to relocate its positions to red one, यहाँ पे आएगा, and this red one is going to flip to green one. That's why here we have written the contribution 0. Whereas in case of xz and yz, always remember they are not going to be changed. That's why the contribution is 2. So you have reduced the molecule with respect to the atom. So here the basis set you have prefer is the atom, and you have reduced your whole point group. Now, next is again what we will do, we will solve this molecule, right? For example, we will apply the reduction formula, and I am taking the first character, that is A1G. Now, in what way you can write it? 1 by 8. What is 8? 8 is the order of group. How do you calculate? You have to add all the number of symmetry element present in a given point group. So if you will add it, you will get the H. The value of H is 8. Now, 1, it is taking from A1G, right? And another A1 we are taking from the character. R, the number of symmetry operation with respect to that particular symmetry element. So that is 1. And 2, you have just solved it. So now you can put all the value and you solve these equations. So what it comes? It comes A1G is 1. Similarly, if you will apply for rest of the irreducible representations, out of them only B1U is present, right? So which two irreducible representations you have find out with respect to the reduction formula? These are A1G plus B1U. Now, see, till now we have reduced the molecule R. We have find out the reduction formula by applying the basis set of atom, and we came to know that the A1G and B1U, these are the two irreducible representation which are present. Now we are moving towards the formation of Salk equations, and in that, if you will remember, we need to apply the projection formula, right? Earlier, if you will see, we were focusing about only two atoms, are the peripheral atom, are the coordinating atom, are the ligand atom. So in case of BeH2, the peripheral atom is hydrogen, right? And what is the central atom? Central atom is beryllium, which I have shown here with the blue shade, right? Now, in the left hand side, I have given the bond length S1, and in the right hand side, I have given the bond length S2. Now, to find out the projection formula, I told you, you need to apply the same symmetry element to see what changes are going to be happen with respect to the bond length. Now, let us see to it. These are the symmetry element E, C2Z, C2Y, C2X, I, sigma XY, sigma XZ, sigma YZ, that we have taken from D2H point group. Now, what is our job? With respect to S1, I have written tau S1. So with respect to S1, we will see what changes are going to be happen on operating this symmetry element. For example, for the symmetry element E, you tell me what will be the fate of S1. Someone from a student, please let me know. If you are going to operate E, whether S1 will be remain S1 or it will be changed to S2. Just think, you are trying to rotate the molecule with the 360. In that case, of course, your atom or your bond is going to retain its own position. That's why the contribution will be S1. Now, with respect to C2Z, remember, we have taken Z axis in this direction, right? So what would be happen? There will be a no change. With respect to C2Y, right? Let us draw the axis for your convenience, actually. Otherwise, you will be get confused. This is Z. This is Y, and this is X. X. Now, let us do it. So till now we have, for C2Z, it is quite convenient. say that S1 is not going to be changed. What about C2Y? Of course, it is going to be changed. That's why I have written S2. So with respect to this axis, if you will rotate the molecule, right, what would be happen? This bond is going to occupy this positions, right? So S1 इधर आएगा और S2 उधर जाएगा. I have written S2. Now with respect to C2X, again same, it is going to reverse. So again it is S2. With respect to I, again S2. Sigma XY. Now sigma XY is the plane which is perpendicular to the Z axis. So basically it is going to be passed through the beryllium. Now in that case, S1 will be the mirror image of S2. That's why the contribution I have written here is S2. In case of sigma XZ, now sigma XZ, this is X actually. Sigma XZ is this one, right? Now see, in this case, if you will see, basically the changes are going to be happen with respect to the y-axis, and that's why S1 is not going to be changed. And if you will see in sigma YZ, again S1 is not going to be changed. Okay, so you have now perform the symmetry element with respect to S1, and you came to the point that these during this symmetry element, in some of the cases S1 is transformed to S2 and S2 is going to transform in S1. Since we are focusing here only one bond length, that is S1, so we have made the table of it. Now we will apply the projection formula. So what projection formula speaks about? You have to find out 1 upon 8. 1 is the number of symmetry element. A, the character of that particular irreducible representation for A1G. And S1 is the fate of that bond length. So now this way you will solve it. So it will come 1 by 8, 4S1 plus 4S2. If you will solve it, it will be 1 by 2, S1 plus S2. For Salk equation, I will tell you need to take the root of the coefficient present for S1 plus coefficient present to S2. So I can write it as 1 by root 2 S1 upon S2. Okay. Now, this is the case. This is a pictorial diagram for this particular Salk equation. That is S1 plus S2. What does it correspond? It corresponds that both bond lengths are having the same phase. And that's why I have depicted them with respect to the white color, or you can say colorless appearance. Okay. Now, we will apply for the B1U, which we have got it from the reaction formula. Now, if you will apply this and solve the equations, you will come across that the Salk equation for B1U is S1 minus S2. Now see, one is having S1 and the second one is having S2, but they are having opposite phases. So that's why one I have taken with a shaded way and another we have taken in the unshaded prospect. So these are the basically Salk pictorial diagram for the Salk equation, these two. Right? In the first one, both are having unshaded. In the second one, one is having shaded and second one is having unshaded. Why? Because the Salk equation for that particular equation is S1 minus S2. Clear hai? Now let us move ahead. Okay. Now, till now, whatever you have performed, basically, you have performed with respect to D2H. I told you why do you have done it? Because to make it convenient to perform the symmetry element, we have find out the subgroup which are having the same characteristic as of the higher Pointer group. So we have taken D2H. Now we are talking about BeS2, beryllium hydride, right? And in that case, the point group is D infinite H. So what we will do now, we will transform the D2H into the form of D infinite H. So in that case, if you will remember, in D2H, we have find out the Salk equation for A1G and B1U. Now, if you will solve it, actually it will come with respect to sigma G plus and sigma U plus. Okay, and this is the reduction formula. This is a reduction formula you have applied it in the very beginning, right? Now, see, you have calculated the two Salk equations, right? One, they are in the same phase, and in the second one where they are having the opposite phases, right? So what atomic orbitals are available? So if you will see with respect to the beryllium, what atomic orbitals can be possible? 1s2, 2s2, 2px, 2py, and 2pz. Right? So what we'll do, we will write all the atomic orbitals here. 2s, 2px, 2pyz. Okay, and we will label them. See, this labeling we have taken from the point group. I told you in the right corner, if you will see, the orbitals are already mentioned in the point group. So from that particular table, we are taking these atomic orbitals and we are labeling them. Okay, even in a general prospect, if I would ask, beryllium is having atomic number 4. What will be their electronic configuration? You know, it is 1s2 and 2s2. So you know, in the valence shell, how many orbitals are already available? It is s and p. Okay, so that is that particular orbitals have been jotted down here. But anyway, don't be get confused. You can think about these 4 orbitals I have taken from the point group, are the character table of that particular point group, and with respect to those orbitals, I have taken directly the labels which are mentioned in the character table. Now see, with respect to this salk, where both hydrogens, or you can say S1 and S2, are having a same phase, right? Now S, you know what is the shape of S orbital? It is a spherical. If it is going to combine with this, there are the two possibilities. One, S will have the same phase as it is mentioned, like they are unshaded region. And second one is a possibility that it may have the opposite phase. That's why I have mentioned both the two. You see this. The central atom, beryllium. Now S can have the same phase as of the salk. So in that case, this will be the pictorial. Whereas there is also possibility that the central atom or the s orbital is having the phase difference from the Salk equation. Then in that case, what will be the pictorial? This one I have written with the black. Right? Now let us find out with respect to the second Salk equation first. So here, if you will see in the pictorial, both H are having the different phase. So always remember, you have to first construct the MOs of bonding parameter or the bonding prospect. So in case of bonding prospect, whatever the shaded region are there, it will try to be get combined or attract towards the same type of phase. So PZ, if you will remember, right, this one is the PZ. So this is unshaded region. So what it will try to be get combined with the unshaded, and this shaded will try to combine with unshaded one. What is the second possibility for anti-bonding orbital? Just reverse it. Now see, it is unshaded, then shaded, unshaded, then shaded. So now the number of nodes are more, right? So it is highest anti-bonding. Okay, which are left? Actually 2px and 2py. I already told you px and py is perpendicular to the z-axis. I have shown the depictions for the Cartesian axis in this case, right? Now see, with respect to the px and py, this is the orientations. You see, it is perpendicular to the plane of yz, and py is the perpendicular to the z, right? Now, have you calculated any salk which can have the same geometry with respect to these orbitals? If you remember, no. You have calculated only these two salk. In one of the salk, they are having the same phases. In another salk, one is having, both are having opposite phases. Other than that, you have not calculated, right? So what we can do, this px and py are going to be act as non-bonding. Okay, let us make the MOT diagram first. Now, available atomic orbitals of ligand you have calculated are A1G and B1U, right? Or you can say sigma G plus and sigma 2U plus, I guess, for D infinite H. Yeah, sigma G plus and sigma U plus. It's of your choice, whichever the irreducible representation you want to apply, you can apply it. I already told you the logic behind it, right? Now see, these are the available AOs of ligand, or you can say the hydrogen atom in this case. Now see, available orbital on the beryllium atoms are A1G, B1U, B2U, and B3U. Okay, now these are the atomic orbitals, right? This is for the first Salk equations. In that case, what are the metal ligand bondings are possible? Now see, the central metal atom, it is beryllium. It can either have the same phase as the atomic orbitals, or it can have the opposite phase with respect to the atomic orbital. So both I have made it. So first one, if anyone will ask, it will have a bonding characters, whereas this one is having anti-bonding character. Why? Because node is going to develop, right? Now A1G correspond to 2S, B1U, 2PZ, B1, this one will be B2U. Please pardon me, it should be B2U. It is 2PX, and B3U, it is 2PY. Now see, this is the MOT. If you will see in the left hand side, I have drawn the atomic orbital ligand systems. Yeah, atomic orbitals are peripheral atoms. In the right hand side, I have drawn the central atom, that is beryllium. Now, you have calculated that with respect to the peripheral atom, which are the orbitals are going to be contribute. This is Ag and B1U, right? Whereas in case of beryllium, which are the orbitals which are going to contribute? These will be A1G, B1U, B2U, and B3U. Now to construct the MOT, your main motto to club up the orbitals of same symmetry. Now see, first it is A1G. So what you need to find out? You need to find out the orbital of the same symmetry which is having the A1G configuration. You see this A1G. So, and you know the basics of MOT, whatever the number of orbitals are going to combine, same number of orbitals are going to be formed. So here two orbitals are going to be formed, one from ligand and another from central atom. So two orbitals are going to be formed. One is a bonding and second one is a anti-bonding. You see this, right? Okay. What is left? It is B1U. Let us see whether B1U is available with the central atom or not. Yes, of course it is present. So what we will do? We will combine it with the B1U. You see this B1U. Now again, two orbitals are going to combine. It means two are going to be formed. So one is a bonding, another is anti-bonding. Okay. Now, is it any orbitals are available on the left hand side? No. But only vacant orbitals which are available in the right hand side are B3U and B3U. So what it will act as? It will act as a non-bonding orbital. That's why it has been kept it here. Right? Now let us make the diagram of every bonding and anti-bonding orbitals. Now A1G is the highest symmetrical orbital where the number of node is 0. And if you will remember, I have showed that with respect to the fragment orbital, there are the two phases or there are the two Salk orientation. One is in phase and another is out phase. In phase may have the probability to be get combined with the central atom of the same phase, and that's what I have make it. All are unshaded. And another possibility is that the central atom will have the different orientations. So in that case, it will have the shaded region. Whereas in case of B1U, now in this case, what we are going to find out, we are going to combine the second Salk equation, where one is having shaded, another is having unshaded. So first job is bonding. So bonding means lower node. So what we will do, we will try to combine it with the orbitals of same phases. Now see, dark is going to combine with the dark and unshaded is going to be combined with unshaded, right? And with respect to this, anti-bonding will be opposite where highest nodes are there. So this way you can calculate, you can make the pictorial diagrams of the bonding orbitals.